All right, so when you open up this file, you're going to, oh, actually, let me close it and open it again. Oh, no, pass them around, because they're on this side, on that side, probably not. Right? Did you guys all get one? Oh, no, I lost it. Where'd you go? Okay, so you see something like this when you open up your graphing calculator file, right? And you've got this like red dot here, right? So what you can do is if you click on it, you can move it around, and notice as you move, the values of A and B change in correspondence to like the x coordinate and y coordinate of the point as you move it. And then notice that this equation, a squared plus b cubed minus 2ab, the corresponding output for the given a's and b's gets spit out, right? And so what I'm asking you to do on that handout is to find all the values of a and b that make that this equation of a's and b's equal to 7, right? So let's see if I come. Am I getting closer to 7? Getting closer. Okay, so about here, that's pretty close, right? So I would plot a point right here where A is like 1.8 and B is 2.3, and I'd record that point on my graph, right? And then I'd go hunt for another one, okay? So I want you guys to take some time and hunt for points, right? Values of A's and B's that make the equation equal to 7. Okay? So you can partner up and try to tackle this faster with a partner if you want. But everybody should have a screen. Are you guys starting to get a feel for a bunch of points that satisfy this equation? Okay. Is anybody finding this really tedious? Huh. Okay. So how can we use our brain? So we want to find all of the points that satisfy the equation a squared plus b cubed minus 2ab equals 7. That's what we want to find, right? So I've done a little bit of the grunt work, but I got bored too. So I can see like what I've plotted 5, 6, 7 points. Some of you guys probably had a lot more than me. So let's focus for just a quick second. What is the meaning of one of these points? So like I've got this point right here, right? It's like negative 2.4, comma, I don't know, 0.2-ish, right? So what is the meaning of that point? What do I know about it? Arian? Okay, so you're thinking about inputs and outputs. So when do we use the language of inputs and outputs? What kinds of things are we talking about? Functions, right? So the only thing I've handed you is an equation, a squared plus b squared, or b cubed. Let's see. Go ahead and write it, right? So I gave you this equation and asked you to find points that satisfy it, right? Points that make it true. So when I look at this point, negative 2.4 comma 0.2, what do I know about this x and y coordinate? How did I come up with it? How are we finding these points? Yeah. They have what? So we're hovering around 7. Like, what's this? What's the 7 though? Where did the 7 come from? I didn't give you a function. I gave you an equation. Wait, I heard something. Say it louder. When the equation equals 7, we're looking for x and y values that make the equation equal to 7, right? So, right, because over here, I didn't have it actually said equal to 7. So we were hunting for those values that made it equal to 7 or thereabouts, right? And so when I identify a point, I'm actually identifying an A value and a B value such that when I plug them in, they satisfy this equation, right? They make it true, okay? So have I found all of the points? No, right? Can we think of a faster way to find all of the points using the technology that we have? In particular, notice the activity that we've done so far has been for this specific value of A and for this specific value of B, this formula equals some value. And then I'm like tracing around and figuring out when that value is 7. Right? But I want all of the pairs that would equal 7. How could I represent that? A graph? Okay, so what do I need to do in order to be able to graph in Graphing Calculator? I need, because I can't graph right now, right? The graph button's not highlighted. Why not? There's no y's and x's, right? So what could we do if we want to find all of the ordered pairs x comma y such that x squared plus y squared minus 2xy equals 7? Oh, that sounds tough. Okay, let's put that idea on hold. And okay, so literally what I just did, right? This is beautiful. Remember, if you write something down, if you can write it down and have it be mathematically valid on paper, then it will be mathematically valid in Graphing Calculator. So check it out. If I type in that equation in terms of x's and y's, and then graph it, oh, ha, ha, right? Now we are looking at what? Am I looking at, what am I looking at? An equation? A representation of all of the points such that? Okay, so this is another one of those mouthful things, right? I can't say that this represents and then one word, okay? That's not going to happen, okay? So the thing that we're looking at represents the collection of points that satisfy this equation, right? So once again, if I identify any point on this curve, right, and I ask you what does it mean, or what does it represent, you're going to tell me what? Well, if I just highlight one point, this is no longer a collection of points, but it is a point that, if I plug in the x and y coordinates, they satisfy this equation, right? How are we doing? Notice I have not said the word rate of change, derivative, integral. We have none of that, okay? This is definitely making sure that we understand graphs and equations at the moment, okay? So, but it would be nice to talk about calculus today. So what if I wanted to throw in those words? How would I talk about, well, before we even get there, actually. So this is a graphical representation of a collection of points that satisfy this equation, right? If I highlight a point somewhere out here, what can I say about this point? It's a point. Can I say anything about it in relation to this equation? The coordinates do not satisfy the equation. That's about all I can say about it, right? Not too interesting. Okay, so we don't care about it. All right. Now, when I look at this graphical representation, it's representing something, right? We just said it's the solution set to this equation. Now, what we're used to talking about are things like functions, right? And we talk about graphs of functions. Is this a graph of a function? So I see people saying no. Can you give me a justification? It doesn't pass the vertical line test. What does the vertical line test tell us? Okay, so that would be a violation of being a function, right? So if for a given, so let's say like at x equals 3, right? There's more than one output for that input. If you're thinking about x's as the inputs and y's as the outputs, right? So I'm not talking about output in terms of the output of a function right now. I'm just using that word to refer to y coordinates, okay? So this is not a representation of a functional relationship between x and y, okay? Now, something I would be curious about, though, is whether or not I can still talk about the rate of change, okay? So if I just stopped my sentence there, hopefully you would say, Stacy, your sentence is incomplete, okay? So when we've talked about rate of change so far, we've always been talking about the rate of change of what with respect to what. How? Changes in y with respect to changes in x. Awesome. So my question now is, can I talk about the rate of change of y with respect to x for this relationship? Whoops. So what was rate of change again? When I want to talk about rate of change of y with respect to x? Yeah. So you're thinking back to like when x is 3, I've got 3 different points that I can see. There might be more if I were to zoom out, right? Okay, so it can't be that simple, right? But what if I were to zoom in and just focus on this point? Can I talk about rate of change now? Yeah?
I feel like it would get squirrely if you try to go backwards.
Okay.
Like rate of change function is just going to go like step by step.
Mm-hmm.
And like it's not going to know like, okay, now you start going backwards on the x.
So I want to highlight something that you just said. You said a rate of change function, right? I have not said the word function. I've just asked, can we talk about the rate of change of y with respect to x? I'm not talking about a rate of change function anymore. I'm just talking about the rate of change. I want to know about it, right? Rashay, did you have a question? So, okay. So I think you're still aiming for function, right? So you want to define this curve in pieces that you can handle nicely. Okay. Well, so we can talk about the rate of change of y with respect to x without having to have y be a function of x. Okay? And that's what we're trying to do right now. Okay? Is I am presenting you a scenario in which x and y are related, right? They're related by the equation right here. Okay? So they have a relationship. You can talk about their covariation, right? As x increases, y does things, right? And you can talk about that relationship between these two quantities, okay? But it's a relationship. It's not a functional relationship, okay? So we've deviated now from the safe land of functions, okay? We're going into more interesting things, okay? So, but what I want to emphasize is all of the foundations we've built still apply, okay? So even though we're not talking about a function anymore, we can still talk about the rate of change because we know what rate of change is, right? We can talk about rates of change of y with respect to x in terms of changes in y relative to changes in x. That hasn't changed, okay? So then the task becomes, how do I do that? Okay, well, we've already decided that we can't do that in general for any given x, right? I have to actually nail down a point that I want to focus on, okay? So if I choose this point in this box, how might I investigate the rate of change of y with respect to x around this point? Yes. Restrict the range. So yes, so let me go ahead and let's see. I'm going to highlight that point and I'm going to zoom in. Okay, now it looks like a function. Forget the rest of the picture for a moment. We've zoomed in. Okay. How would I find the rate of change at this point? Yes. Draw what? Tangents. Okay, so you're talking about finding changes in y over changes in x. Yeah, I like it. So, all right, what can I do? I can say, here's my point. It's at 2.9656, comma, 2.267, okay? If I want to approximate the rate of change, I can do so by just finding another point nearby, right? This is what we've been doing. So a little change in x will have a corresponding little change in y, right? So so the next point on that curve, well, not the next point, but a nearby point would be 2.998, comma, 2.262. So what's the rate of change? Take a second to figure it out. And you have a calculator right in front of you. I suggest you use it. Oh, Shelly, you're killing me.
I know. You're one point now.
truly hurting my feelings with the TIs. You have a calculator on your computer screen. Okay, so what is the approximate rate of change? Negative what? 6.48. Seriously? I'm really not buying the negative 6.48. 154. Okay. Why am I not buying the negative 6.48? That's way too steep, right? Because, all right, so let's remind ourselves, what is the meaning behind this number? So this number is what you're telling me is the approximate rate of change at this point on the curve, right? What does that mean? Rate of change. So that is the rate of change, but what is the meaning of the rate of change? Yes. So for every change in x, the change in y is negative 0.154 times that change in x, right? So if I were to zoom in even further, which I'm not going to because it'll make all of our writing look weird, right? So, but like you can imagine, right? Here's a change in x and a corresponding change in y, right? And so this number gives you, we got that by doing change in y over change in x. This number represents the relative size of the changes in y with respect to changes in x. Foundations, right? We spent a lot of time building up this idea. Don't let it go, okay? So that was a lot of work, right? And all it did was give us the rate of change at one point. And remember, we had like 3 different points corresponding to an x value around 3, right? So it would be awfully nice if we had a formula to do this for us, right? Because I don't really want to go through this process for every single point on a curve. You literally couldn't do it, okay? So it would be nice to have a formula, right? Now, earlier, some of you guys sounded like you really, really wanted to have y in terms of x, right? So let's think about that for, about 0.2 seconds, okay? So if I look at the equation relating x's and y's, how easy is it to solve for y in terms of x? It's not, right? So you've got a cubic in y and then an x times a y, and I'm not saying it's impossible. You can. There is a general solution for a cubic. It's gross, though, and it would be just gnarly, and nobody wants to go there, okay? So solving for y in terms of x is not an option, okay? But as we just saw, that doesn't mean we can't talk about rates of change, okay? So what I can do is say to myself, well, in theory, y really is some function of x, right? But I don't know what that function is, right? And I'm not going to waste my time trying to find it because it's going to be gross and it's going to be laborious and I just don't want to do it. But I could imagine, right, that y could be written that way. And so if I imagine y as a function of x, then when I look at the equation x squared plus y cubed minus 2xy equals 7, then this piece, the y cubed, is now a composite function, right? It's some function of x raised to the 3rd power. And this 2xy is a product of 2 functions of x, right? The first function would be 2x, and the second function is y. So let's see about applying all of the rules that you guys have memorized for tomorrow's mastery test. to this situation. So I want to find the rate of change of y with respect to x. So if this is the relationship, this whole equation is the relationship between x and y, if I want to find the rate of change, well, the rates of change of the left and right sides should stay in the same relationship. Okay? So I can take the rate of change of both sides and have this still hold. Okay? Are there any questions about this? Is my notation clear and what I'm wanting to do clear? Okay? So this, again, this top equation is the relationship between x and y. If I want to find the rate of change of y with respect to x, then I can find the rate of change of that relationship. Okay? So let's go ahead and do it. So overall, this structure is a sum of functions. So in order to find its rate of change, you can find the rates of change of the pieces. So what's the rate of change of the first piece? 2x. That was the easy one. Okay? Now I've got this y cubed. So again, remember, what did I say? Y, we're thinking of it as a function of x. So when we look at y cubed, we should think of this as a composite function, where the inner function is y and the outer function is the cubing function. So how would I find the rate of change of this? I heard mumbles. Got to be brave. Yeah, it's that rule, the chain rule. Help me out with it. 3y squared. So this is taking the rate of change of the outer function with respect to the inner function. Finish it? Times the rate of change of the inner function. I like it. Question? So y cubed is different from x squared because we're thinking of y as a function of x. Yep. So remember we said that in theory we could solve for y in terms of x. But rather than doing that and having some horrific equation to work with, right, we can just think of it this way. And when we think of it as a function of x, then whenever we see a y, we're really thinking of it as a complicated function in terms of x. Okay? Does that help? Okay. All right, so that takes care of the second term. What about the third term? How should I think of this? 2xy? It's a product, right? And so I can think of it as the product of 2x and then y, right? Because y, again, is some function of x, okay? So then product rule tells me, sorry, 2 times y plus 2x times the rate of change of y. Exactly. Notice those parentheses are really important. Yes? That's totally fine. You can do that as well. If you wanted to keep the -2 out as a constant, you could have done that as well. Okay? And then on the right-hand side, what's the rate of change of 7? 0. Right? So, okay, well, this still looks like a hot mess. But we do at least have the rate of change of y written in there, right? It's there. And this is a lot easier to solve for than what would have been the case had we tried to solve for y originally and then taken the rate of change, okay? So what we're doing is sort of, instead of starting with y equals and finding the rate of change, we're finding the rate of change and then finding the y prime equals, okay? So let's go, because remember we said it would be really nice if we had a formula to be able to figure out the rate of change at a given point. So, okay, so that means I want to isolate y prime. Do you agree? How do we go about doing that? Okay, so I want to bring the 2x over there. I've also, so notice I've got, the thing I care about, y prime is in this term, and it's also in this term. So what I'm going to combine two steps, if you don't mind, and bring the 2x and the negative 2y, I'm going to move them to the right-hand side. Okay, so I'm going to have 3y squared y prime minus 2x y prime from distributing the negative equals 2y from adding the 2y, and then minus 2x. Why did I rearrange it that way? Well, I don't want to divide by y prime. My goal is to isolate y prime. I'm trying to solve for it. Yeah, I can factor it out. So y prime times 3y squared minus 2x is equal to 2y minus 2x. And now it becomes super easy to solve for y prime. I can just divide both sides by the multiple, right? So 2y minus 2x over 3y squared minus 2x. So now we have a nice, compact, super handy-dandy formula for finding the rate of change of y with respect to x at a given point x comma y. Because notice this formula requires you to know both the values of x and y, right? So it will no longer make sense for me to just ask the question, find the rate of change at x equals 3, right? I'd have to find the rate of change of y with respect to x at the point 3 comma 2, right? Because you need both coordinates to be able to find the rate of change now. Okay. Now, if I were to only give you the x coordinate, what would that mean? You'd probably have to go back to the original to find y, right? So don't forget how to do like old, super old stuff, okay? All right. That was a little bit intense. Yes?
Will something like this be on our master exam?
No. Okay, but so let's check ourselves. So, right, we had this point before. What was the ordered pair that we had before? It was like 2 point, what? Did you guys write it down? 9656. And what was the 2.267? Nope, I just want the one we started with. And so we approximated the rate of change was approximately negative 0.15, right? So let's see how good that approximation was. Let's use the formula, right? So I've already typed in the formula here, right? And notice it's a function of two variables, right? It's the rate of change of x or y with respect to x, but it requires the inputs of x and y, okay? So then if I were to type in that the y value is 2.9656, and then the y value was 2.267, notice that the rate of change there is negative 0.147. It's practically negative 0.15. So we did a darn good job of approximating, okay? But the formula is so much easier if you have it, right? Rather than going through the process every single time, okay? But again, just to remind you though, the meaning of this value, okay? So yes, I can say this is the rate of change of y with respect to x at 2.9656, 2.267, okay? But the meaning of that is that if you look at little changes in x near that point, the corresponding changes in y will be negative 0.14728 times that change in x. Okay, so the relative sizes of the changes in y to changes in x have this value. Okay, this is the relative size. Okay, so don't forget about that meaning. Okay, let's practice doing this one more time with, shoot, I don't know, graphing calculator closed all my stuff. All right, so here's a new function, or not a new function, but a new equation, right, in x and y, and I would like you to find the rate of change of y. This is good practice for the mastery test, even though it's not explicitly going to be on there. You still have to be able to use all these rules, right? Question? The square root is just over the y. Mm-hmm. Question?
Is the negative,
Okay.
is the negative 2 part, is it under the radical?
Nope.
It's kind of hard to see.
Is that hard
The
to see?
size. Do you know how to change that? Go to document
Can I
settings.
just? Oh, no.
I mean, that might work, but I think that works only in text.
Oh,
You can try
okay.
it.
No,
Go to
I won't.
document settings.
Document settings. Wait, where?
Either maybe file.
File.
Yeah.
Document settings.
And you can just change your font size like to 35 or something. The thing is now, every time you
Yeah,
open,
it's gonna make it big.
when you open a new,
Okay.
I don't like that, but when
Yeah.
you open a new file, it'll be that size.
Okay.
But yeah.
Cool. Thank you. I hate to do this because I like the hard work so much, but I just want to make sure that you at least see it one more time because I've used up our time. So when we look at the first term, right? So again, the overall structure on the left-hand side is that it's a sum of two functions, right? So we take the rates of change of the individual pieces and then add them together, okay? So the rate of change of the first piece, negative sine y squared times 2y times y prime. That's a double chain rule, right? Because the rate of change of y squared is 2y. You use the power rule, but the chain rule tells you you have to multiply by the rate of change of y, right? All right. The second term, that's a product. So I can say it's, oh, okay, you want to start that way. X times 2 square root of y times y prime plus square root of y, right? There's a times 1 in there, okay? You don't have to write that. And then minus 0 equals 1 over x. Okay, so then you don't have to write the minus 0. Okay, so then notice this term has a y prime and this term has a y prime. So if I'm trying to solve for y prime, I'm going to keep those on the left. And I might as well, since I already know what's going to happen, factor it out. So y prime times negative sine of y squared times 2y plus x over 2 root y. Okay, so I factored out the y prime from those two terms. And I've got 1 over x minus the square root of y. So I brought this to the other side. Okay? So that in order to have a nice closed form for y prime, now I can just divide both sides. Like so. Okay? And so that is our formula for finding the rate of change of y with respect to x at a given point x comma y. Okay? All right, thank you very much for your time. Study, study, study for the mastery test. It would make me so happy for all of you guys to pass it on the first try. So unbelievably happy. Yes. I'm not posting solutions. Why? Because you can check them on Graphing Calculator, you can go to a tutoring center, you can come to office hours. You've got lots of places. There is a homework assignment for Friday. It's short.
We're still good to take the mastery test.
Yes.
Okay. Thank you.
10:30 I think is when they open tomorrow. Yeah, normal testing stuff.
Hey, so I had